Hi, my name is Jesse, and I'm excited to present our work on uncovering and addressing blink-related challenges in using eye tracking for interactive systems. Eye tracking is becoming more and more popular for all kinds of interactive systems and is now a major additional input for multimodal interaction. On the other hand, optical and infrared eye tracking inherently suffers from data loss. This data loss happens when the eye tracker is unable to identify the pupil from the image as shown on the left. In traditional machine learning, we could use these gaps in data to extract additional features such as blink duration and blink frequency. However, for representation learning models like LSTMs and RNNs, this is not an option, as they cannot work with missing data as input. As such, we came up with two research questions. What are the current methods for dealing with missing data, and what is the effect of these methods on the data quality? To answer this first question, we conducted a structured literature review to identify a wide range of approaches to use with eye tracking data. We followed the PRISMA guidelines to review prior work, which is well known in the HCI domain. In this review, we aim to identify methods used for handling blinks, the use of blink detectors, meaning how blinks were identified, and the task that was used for this study. We explored two databases, namely the ACM Digital Library and IEEE, for a total of 399 records. After applying all our exclusion criteria, we were left with 140 studies to be included in our review. From these 140 studies, 44 papers did not report on how they dealt with missing data from their experiment or acknowledge the existence of it. 16 additional papers had insufficient information to be fully included, as they had no handling of the missing data, or they simply said they would remove blinks, but they did not define them. Out of the 81 papers that were remaining, 16 simply said they would remove missing data, 19 applied linear interpolation, and so on. Notable is that 73 out of these 81 papers classify missing data as being a blink, even though some of these works had parsers available from the iLink or the SMI eye tracker. It is additionally noteworthy that 3 out of these 81 papers excluded additional data surrounding the section of missing data. To go back to the research question, we identified that methods used for blink detection and the way that missing data is processed is inconsistent in the current literature, and improving this has a potential positive impact on the research replicability and quality. When removing missing data, it is clear that this would help with the overall performance of representation learning, but it could also result in a major loss of available data. For the infilling methods, it is clear that there is a lot of options. However, there doesn't seem to be a consensus of which method is preferred. This could lead to not only inaccuracies or wrong interactions, but also a low reproducibility. So we wanted to investigate what the effect of these methods is on the data. To investigate this, we acquired 11 different open source datasets, all part of peer-reviewed work from various venues, all available online on either GitHub or OSF. We first processed the data such that it is all in a similar format, meaning that if there was binocular data available, we included only the left eye, as not all datasets came with binocular eye tracking data. All gaps in timestamps of more than 1 second were split into different parts, as these could be indicators of the end of a trial or a break during the experiment. Whenever there was missing data, we considered this to be part of a blink, excluding those where there was a single sample missing. As we were unable to identify a dataset where both eye tracking data and a video stream of the eyes was available, we needed to verify that the missing data in the datasets was due to blinks. We verified this by recording our own data using a high-speed RGB video stream and the eye tracking data from an iLink 1000 Plus. We first explored the datasets. Here we show the blink frequency in blinks per minute on the top and the time between blinks in milliseconds on the bottom. It simply verifies an established finding that there is a lot of factors impacting the blink frequency. We also explored the closed eye time. We were able to fit an inverse Gaussian distribution over the normalized frequency, as shown in the lower figure. We visualized the distribution using the striped lines. Next, we investigated the noise before and after missing data, as you could see to the left of me. It shows the data from the different datasets and the reference data, where we know that this represents blinks. We can see that there is a sudden increase in speed and variation of speed as we approach to the missing data. The horizontal dashed line represents the mean speed and mean variation of speed of the first half of the graph. The vertical dashed line represents the divergence from the horizontal line. We can use these vertical dashed lines as potential cutoff points, as from where the eye tracking data is affected by the movement of the eyelid. Similar to the last slide, we can also look at the data after missing data. Again, the horizontal dashed line represents the mean speed and mean variation of speed of the second half of the figure. The vertical dashed line represents the point of convergence. We can again use these vertical lines as potential cutoff points as to which the data is affected by the movement of the eyelids. To put the vertical lines into numbers, we've shown that eyelids movements can affect eye tracking data up to 70 milliseconds before missing data occurs and up to 118 milliseconds after missing data. Then let's have a look at the method to simply remove data that contains blinks. To do representation learning, we would need to feed in a window of data. These windows are simply consecutive points of data without any gaps, without any missing data. We represent this here on the x-axis as time. As visualized on the left, as soon as we hit 5 seconds of these window sizes, we would lose about 50% of the data from being useful. We also investigated the step size of these windows, whether or not the window moves a single data point, half of the window, or the whole window. Here we observe no noticeable difference. Lastly, we investigated the impact of different interpolation methods, namely linear, third and fourth order polynomial interpolation, and cubic and normal spline. To evaluate these against the ground truth, we created artificial blinks using the distribution of blink duration and the cutoffs mentioned earlier in the video. We then calculate the mean distance between the points generated by the interpolation methods and the actual data points, so the ground truth. Here we found that linear and cubic spline interpolation has the least amount of mean distance from the ground truth. Then as takeaways from this talk. We have shown that as window size increases, the likelihood of a blink appearing in this window naturally follows the same trajectory. It also increases. If we simply remove missing data, this can lead to a massive reduction in available data for representation learning purposes and can cause delays in interactive systems. As such, our first takeaway is that we should simply not remove missing data that contains blinks. What we should do is that we should inspect the data surrounding blinks. We have shown that there is a high variation in the data just before and after a blink. We should inspect this and remove this if necessary. Lastly, we have shown that from the interpolation methods, linear and cubic spline interpolation perform closest to the ground truth data. We recommend that you should use linear or cubic spline interpolation to infill within blinks. Thank you so much for listening. If you have questions, please reach out to us or scan the QR code for more information.